VP of Engineering at Riverlane. What I'm gonna, I'm an engineer. What I'm gonna talk about today is what the quantum computing and how exciting it is, at least for me and for everyone at Riverlane. I want to start with something that is probably not familiar and move into what we're doing. First thing that you're not aware of, you're probably aware of lots of really complex mathematical problems, and what's so-called NP-hard type of computations. And what you think of is probably bitcoins, portfolio optimization, apparently Pac-Man, as I discover. But these problems, as in particular Pac-Man, doesn't really have much application, much impact in your life. There are other problems that have the same sort of complexity, and they are really challenging. And they do have an effect on your life. I'll mention two. One is, interestingly enough, is the fertilizer production. So globally, we consume about 1-2% of all the total energy to generate fertilizers, global energy. This process is particularly not effective in terms of energy requirements. Tiny prokaryotes in the soil can do that at under 1/100th of the energy required, but we don't know how. We have ideas, but our simulation of the process is not good enough, so we can't really recreate the same process in our labs. This is considered an extremely complex problem that is quantistic nature for different various reasons. And similarly, another one is drug development. So drug discovery is about estimated that it takes 2.6 billion to produce a new drug. Most of the cost is in the initial stage and of the discovery, then the human trials, the animal trials, etc. Failure rate is really high, and this because there is the modeling of the proteins, of the enzymes is not up to the task. And this is again because it's, lots of quantistic and atomic properties of this molecule are affecting the process. As you can imagine from all this mentioning of quantum, how quantum computers can help. They can in looking at these examples or similar examples. If you have a problem that is what is called with exponential runtime, so the time it takes is a function of the number of inputs or the size of the input. You get something like this table. So classical, not quantum, will take the age of the universe. This is probably an example that relates to factorization of prime numbers. And a quantum computer can do that in 25 minutes. So obviously, it's a special type of problem. There are lots of problems like this. And watch out here, because this was my initial mistake before joining Riverlane. Not all the problems are like this. So there is a set of problems for which a quantum computer on the right is a monster, is the fastest thing that can go. But there are problems in which you want to turn, steer, park, and the computer, the classical computer on the left, is much better. So quantum computers are really effective in a set of problems, and there are different speed ups that you can achieve. So this is like sort of the pyramid of performance gain that you can get. And at the top at the pinnacle of this pyramid, there is things that are really accelerated by quantum computers exponentially. And at the bottom, there are things that are accelerated by a factor of 10, 100. And we do care a lot about this bottom of the pyramid, because this is where you find stuff that make drugs discovery possible, that makes the fertilizer production more effective. And this is where all the pharmaceutical company and all the money are now initially moving. So we are in in what's called NISC era. So we are in a phase in which quantum computers are still clumsy. And what they can, and we are in the yellow area. We are moving towards the green one, in which there are applications that can already benefit from quantum computers. And then we will be in the blue era in 10 years' time, in which all the applications that need a ultra-fast supercar are possible. Now, just to motivate the yellow, green, and blue, there are some roadmaps made public by IBM and IonQ. IBM, IonQ is the biggest company, the second biggest company in the US quantum computing wise. They have quite a large portfolio of machinery and applications, and they both claiming that they will reach this stage of being able to do something commercially important and effective in about 5 years' time. The investment is exploding, so we are about 1 billion, and this is from 2 years ago. So numbers keep kind of doubling every year or so. And hoping this is an appetizer, a good appetizer for you now. Where do we sit? Where is Riverlane? What do we do? So Riverlane is traditionally a computational chemistry-based oriented company. And our goal was to get to tick all these boxes and do cool things with quantum computers. And then we discovered that the software was not good enough for us, and then we became a software company doing quantum software on top of chemistry. So what do? Is we trying to work with all the possible quantum computers in the planet. There are about 32, let's say, commercially ready quantum solutions, and of different type of technologies, completely different constraints, completely different problems to solve that they can solve, and problems that need solving to make them viable. And they all have in common the similar structure. That is what makes the engineering part of working at Riverlane super exciting. They have these ultra complex heterogeneous systems with CPUs, programmable logic, so FPGAs, custom logic as ASICs, superconducting logic, optical, radio frequency, everything you've seen in a book in engineering is kind of needed. And but they share this heterogeneous structure, and this is important to us. And what do they share is also the concept of wanting to implement quantum operations. You might see these pictures in my slide, but the idea is that there is a big branch of quantum computation that is still looking at numbers and operations and formulas. This needs to get close to reality and work with the hardware. So we are creating this connection between writing formulas and getting them to be executed on a quantum machine. So, for example, this lovely music chart is in reality a tiny, really, really tiny way to characterize them, and is only part of it, to understand the energy of H2 hydrogen molecule and the way that the electrons are interacting, and that can be done with a quantum computer. Obviously, this music chart is much longer. All these blocks are something that in the Google chip that is on the left, the Sycamore, becomes something really electronics focused and driven by lots of different hardware and software units. And this is just the beginning, because then people understand that to operate these machineries, we need to reach the same level of correctness that you have in your current system. And so they need error correction. They need a way to trust the data. And this problem is much more tricky than in classical, and is something that there is no framework yet to do so. But this is where we stand. This is what we do. We try to tackle the focusing on chemistry and materials, we are trying to develop all this framework. So from the top, we understand that we have small quantum computers now, but we can mix and match quantum computers and classical computers to get the best of both worlds, and show that we can build and simulate better existing things. So in this case, we are simulating part of a molecule with a quantum and everything else with a classical machine. We want to allow all these hardware companies to win, because we believe in a democratic market in terms of hardware companies. And to do so, we have developed our framework for testing, developing, and targeting these heterogeneous systems. We do run on hardware. So this is a lovely scan from our friends at Oxford Ionics, in which we run an experiment on their quantum machine. Nothing crazy. And the cool thing is what we have done is all our code is Python-based. So we use the power of simplicity of Python, make all the physicists happy, but by leveraging these capabilities. And we want to move to a new paradigm in terms of controlling these complex quantum machines with our control stack. We work with the last thing that we do is, well, one of the last public things we do is to work with all the hardware companies in the UK, the quantum hardware companies in the UK, and we are trying to design the new API, let's say, that is needed to talk to quantum computers. As you can imagine, we are growing and we are looking for people, so please do check our website to see if there is any role that you might find intriguing, and give us and send us a message. That will be really appreciated. And here's my mail, and thank you.